Let's solve the second question for review of chapter 5. We have a nozzle that a jet of air going to it and then sticks to a stationary pellet that you can see in the figure here, and then also come out of V2 and V3 and these two pipe. So the questions, so what we have here, we have the velocity of the jet, we have the diameter of the jet, also, yeah, that's it. And now what we are trying to find is trying to find the anchoring force. So then it means that we need to use the conservation of momentum. So let's write down what we are trying to find. So we are trying to find for part A the anchoring force, which is Fa. The assumption would be steady state, incompressible, constant properties, and then we have 1D flow, we have inviscid flow because it's air, and then we have, and also we can say, because it's to the atmosphere everywhere, right? So we can say P atmosphere acts everywhere. Then we don't need to show it when we want to use the conservation of energy, momentum, right? Now, if I write down the conservation of momentum, so conservation of, so this is part A, right? So of momentum, so if I write it down for, so I'm not going to write down the complete formula, so you know how to simplify that, because it's a steady state, the first term going to be 0, and now I'm going to write it down for y direction. So for the y direction, we have, okay, let me just write down the complete one after considering a steady state. So this is the formula for conservation of momentum after we consider a steady state, right? And this is m dot, as we know, and this is velocity, which the direction depends on the direction of the velocity. Now let's now I'm going to write down the conservation of momentum equation, but first there are some steps that we always tell to follow the step to solve the question, right? So first we need to draw the control volume. So I have my opening here, so I want to have it parallel to that. I always, not always, sometimes, most of the time I'm using the control volume that going to be parallel to the openings. This way we don't have to be worried about, for example, the theta and all the slip. So then also it's going to be, because if I draw it like this and the velocity is coming out of this, so it's perpendicular to that, right? But if this is the tube, right, the pipe, and then the velocity is coming out, if I just draw the control volume in this direction, right, and then my x, y, let's say this is that, then this is not perpendicular, so you need to consider the sine theta and cosine theta. So to ignore that, you can just simply draw it to the way that the velocity is perpendicular to your control surface. So oops, it's really red, so this is my control volume, right? Now also we need to consider the direction. Also for direction, if I consider x, y direction as it is, so I need to, uh, for the direction of velocity, I need to multiply them by cosine or sine of theta, right? So to ignore that, I'm going to assume the xy direction in direction of the velocity, right? Because I have two velocity in this direction and only have one velocity in if I just consider xy direction. So I prefer to have this coordinate system. Otherwise, I mean, if you even consider this coordinate system, you're gonna have the same answer if you make sure that you multiply whatever it is by sine theta and cosine theta. So now we have that one, and then let's write it down. So for the anchoring force, I have Fa. So and Fa it's in my y direction, right? So this is Fa. We can see it here. And because of that, I'm going to write down Fa, right? And then for y direction, right, I have, so the velocity that I have here at the jet, this one right here. So let's just let me just write it down here to see how we can, okay, simplify that. So we have Vj here, right? And if I consider, because the x and y direction is this one, right? So let me just, if I consider that one, this is going to be Vy, right? And in x direction, this is what we have for x direction. So this is what we have for x direction. So Vx, and so yes, so this is how we just consider that one. Okay, it's not perfect. Let me just try it again. So I have Vj here, and then so now if I want to draw the component on y and x direction, right? So this one going to be my vx, sorry, and then this one is going to be vy, right? And you know that this, if you look at this one is 30 degree and this one is 90 degree, right? So then it means that this one is 30 degree and then this one is going to have 60 degree, right? Now from here, let's continue writing down the formula. So we have m dot of j, right, and v of j. But Vj has two components. I only need the component in y direction. So I'm going to write it down and as a Vy, right? So now let's see what is their sign. M dot J is inflow. So it means that we have a minus sign. And Vy, if you look at this Vy here, is in the opposite of the y direction right here. So it has a negative sign here, right? But we don't know what is Vy, but we know Vj, and we know also the degree between them. So we can easily write it down. So Vy is Vj times cosine of 60 degree, right? and m dot j is rho vj aj. Remember, in m dot j I have vj, not vy. Remember that. So from here, I'm going to also write down all the values that I have for them. So for Vj, I have 40 meter per second. I have cosine 60 degree. The velocity, I have 1.23 kilogram per meter cubic. I have the velocity of jet is 40 meter per second. I have pi 4 times the diameter um, squared for the area of jet, and from here I'm going to get Fa as 0.7 Newton, right? Try to also consider xy direction as this and solve it again, and you need to get the same answer as whatever I get here. So just try that one, and also make sure that you completely understand this part and this part, all of the sign Vy, and I'm pretty sure you know that one, but just try to practice that. So this is part A, and now for part B, we wanted Fj if plate moves at 10 meter per second velocity. So part B, I want to find Fa if the plate moves at 10 meter per second, right? So when we say that the plate move at this, right? So it means that my control volume is moving. So it means that I need to consider the relative velocity to the control volume, right? So now if I consider the velocity of control volume as 10 meter per second, then V is going to be Vj, which is 40 meter per second, right? And this is what we have for the relative velocity, right? V minus VCV. This is what we have. And from here, we know that VCV is, let's say 10, right? It's 10. And then we have a minus sign, and then VCV, oh, sorry, this one was V. So this is 4D, sorry. V is 4D, which is Vj, right? And then we also have, if the plate is moving, we have 10 meter per second, right? Then from here we get 30 meter per second. And remember that for the relative velocity, this is what we have, the formula for relative velocity, right? And now let's see. So let me just also write down this for you guys. So we know that this is the velocity of the moving control volume, and this one is the absolute velocity, right? And this one is the relative velocity to the control volume. To control volume, right? And let me just see. And we also consider this as positive right here, because it said that, let me just show it here. It said that it's going to be to the right at a constant speed of 10 meter per second, right? So it was like this if I want to show it to you. So the velocity of jet, we have v of j, right here as 40 meter per second. And now we are going to say that the plate is going to the right also with v of cv if we call it, right? So this is 10 meter and this is 40 meter, right? So, and we just have a minus sign here in the formula. It's not the minus sign for v of control volume or the absolute v. So this is why we get 30 meter per second. So now let's so we also write down the control the conservation of momentum when we have the relative velocity, right? Now let's write down the all of the value that we have. So for force, and this time we are going to write down for y direction again. So let me just write down y direction. So for velocity in the y direction, we have the FA again. So we have FA, and then we have WY, right? And we have M dot J. Now let's see what is the sign of them. So, and you know already why we consider y because it's in y direction. So M dot J is going to be again negative because it's inflow, and WY is also going to be negative because of the direction of it, right? So let's just look at this one. Okay, same reason I mean. Now, what is WY? So WY is like how we calculated for VY right here. So WY going to be W times cosine 60 degree, and then M dot J is going to be rho WAJ, right? And if we just put all of the value that we have here, so this is for VY, and then we have for density 1.22 kilogram per meter cubic times 30 meter per second times the area. Two. Okay, now from here what we get for FA is 0.39 Newton. Now it said that in part C, it said that when the plate is stationary, determine the percentage of mass flow rate along the plate surface for each of the two directions, right? Now let's see how can we solve part C. So now for part C, let's we are trying to find m dot 2 and m dot 3, right? So let's use conservation of momentum in x direction. So in x direction, conservation of momentum. And now for doing that, we need to write down all of the forces on x direction. So we don't have any forces on x direction because we don't have, there's no pressure effect on the surfaces on the potential energy. So yeah, this is why we don't have it. So then it means that 0 is equal to b, and the right hand side of the conservation of energy, which is right here. So this one get 0, and this one, let's write it down for all of the sections that we have. So for section, if we consider jet at section 1, right? So we have Vx, which we show it here, right? So we have Vx, and so we have Vx and we have m dot j. M dot j is negative, it's inflow. Vx is positive, and then we have V2 m dot 2. M dot 2 is outflow, it's positive. V2 is in the positive direction of x, is positive. And then we have V3 m dot 3. Let's see the signs. So m dot 3 is coming out here, so it means that this is positive, and then V3 is in the negative direction of the velocity of the x. So this is how we have a minus sign here, right? And now if we look at the assumptions that we made, we said that we have implicit flow, right? So we have when we have implicit flow, we already say that Vj, when we have implicit flow, all of the velocity are the same, right? So there is no when we have implicit flow, we can say that there is no changing in velocity. So this is why we can say that. And so it means that I can easily just delete all of the velocities that I have, because they are the same, right? And now, oh, sorry, not this one is wrong, because Vj is equal to them, not Vx. So if we also just write down Vx as Vx is going to be Vj times cosine 30 degree, right? So then this Vj is going to be cancelled out. So if we simplify and rearrange it, at the end we are going to get m dot 2 equal to m dot 3 plus m dot j times cosine 30 degree, right? And now we need another equation to solve it. So let's use the conservation of mass. So conservation of mass, so it's easily, we know that the inflow is equal to outflow. So for inflow we have m dot j, and for outflow we have m dot 2 plus m dot 3, right? And now if we use these two equations and for example substitute the m dot 3, if we solve this for m dot 3, we are going to get m dot j minus m dot 2, and substitute that one in this equation. So we are going to get m dot 2 equal to m dot j minus m dot 2 for m dot 3, right? And then we have m dot j cosine 30 degree. So from here we are going to get m dot 2 as 0.933 m dot j, right? And also we have that one right here, so we can substitute m dot 2 there, and then this is what we get for m dot 3. So it wanted the flow rate fraction to the flow rate of the jet. So this is what we have for this question.